In this lecture, I want to transition between the topic that we have been discussing, electric and magnetic fields, and move into literally the first topic we discussed this semester, which was light. Okay, I want to begin with stating a new perspective on Faraday's law. So Faraday's law was this idea that when a magnetic field changes, it can induce a current or induce an electric potential, a voltage. And it's visualized here in a totally new way, where the brown lines represent a changing magnetic field. And when a magnetic field changes, it creates a current if there's a wire there. It creates a potential difference if there's a wire there. If it's just air, it'll create an electric field, and that's represented here with green arrows that form circles. I didn't emphasize this connection between a changing magnetic field and electric field earlier because it wasn't useful for anything. Okay, there is a second law or second rule that looks very, very similar. And it says that when there's a changing electric field, that a magnetic field is created. And so in this image, it looks very similar to the last one, but the labels are different. The brown lines are intended to represent an electric field that is somehow changing, and that will create magnetic fields that form circles. Okay, so these two rules by themselves alone might not be very interesting. But when you combine them in a very specific way, they become incredibly common. Okay, so I want to show how that can play out. I have here a radio tower on the left. That's a piece of metal where electrons can move up and down, and one electron is shown there in blue on the left. And what's visualized as arrows is the electric field that surrounds the electron. So an electron will attract positive charges, and so that's why the arrows all point to the electron. Okay, if I can automatically set the electron to move up and down. Usually, like a radio tower will force electrons to go up and down the tower, and that creates an electric field surrounding the tower that's changing as the electron goes up and down and up and down. And you can see that with the arrows here. Those arrows represent changing electric fields. Those changing electric fields will create magnetic fields. I'm not going to add that to this image, in part because it would make the visual overly complicated. But those changing electric fields would create a magnetic field. And those magnetic fields that were created would also be changing, which in themselves would create new electric fields, which would create new magnetic fields, which would create new electric fields. There would be a feedback process. And I can right now, the arrows here are not showing that feedback process. Now I'm going to change it so that just that feedback process is displayed. What you can see is that there's a chain reaction where the arrows, which represent the electric fields, are changing in response to the electron moving up and down. When I stop the electron moving, the electric fields aren't changing at all. When I start it moving again, the changing electric field creates a changing magnetic field, which creates a changing electric field, and it's a chain reaction that moves out. I can isolate the changes to just a line, and the purpose here is to take away all the other arrows because they're getting kind of confusing, and just concentrate on the arrows that are contained along a line between the tower on the left and the tower on the right. And you can see that the arrows go up and down, and if I stop the oscillation, the arrows stop changing. When I start the oscillation again, there's a chain reaction. I'm going to ignore the red line, by the way. Okay, so let's go back to that changing electric and magnetic fields. that combination of changing electric and magnetic fields is exactly what light is. Light is a wave of electric and magnetic fields that are changing. So I have two different visuals here. The upper diagram represents a picture of light that's frozen at one point. And what you see in red are a series of arrows pointing up and down that represent the electric field at different points along that line. And then in blue, you see a series of magnetic fields that are tilted 90 degrees. So they're mostly coming out toward you or going into the screen away from you. And you can see that the magnetic fields are changing as well at different points along the line. So if we unfreeze this, you get the animation that you see at the bottom, where this changing electric and magnetic fields are moving along a line. And as we saw at the beginning of the year, or the beginning of the semester, the distance between two peaks is the traditional way of visualizing the wavelength of this changing this changing series of electric and magnetic fields. By the way, there is a relationship between the direction of the electric field, the direction of the magnetic field, and the direction that the light moves. And you can see that with my right hand picture there, where the fingers point in the direction of the electric field, the palm faces the direction of the magnetic field, and the thumb goes in the direction of light traveling. Okay, so there are a series of ways of describing light. They are all roughly related to how bright the light is. So bright involves more energy. It also involves stronger electric fields. It also involves stronger magnetic fields. The simplest intuitive thing is to just think about how much energy is going into creating the light every second. That's called the power. Oftentimes radio stations are described according to how much power they're using. Or for that matter, light bulbs. A 60-watt light bulb uses 60 watts, that is 60 joules every second, in the process of creating the light. So a second way of describing light is how bright it appears as you move away from the light bulb or the radio tower or whatever is producing the light. And generally, in most situations, or the convenient thing to convenient quantity is intensity. So that's, I don't want to get too much into it, but it's kind of describing how intense the light is as you move away from the power source. And that intensity is described in that equation in the lower left. We could also describe the strength of the electric field that's making up the light, or the strength of the magnetic field, which is making up the light. Both of those are related to intensity, and you can see that those equations to the right. So those are just different relations for describing the strength of light. There are, of course, many types of light that are different principally in their wavelength. So visible light is described with that rainbow seen at the bottom here, between roughly 400 and 700 nanometers, and that takes us from purple to red. And then we can go to longer wavelengths, longer than red, which is infrared and radio waves, and we can also go to shorter than violet, so that's ultraviolet, X-rays, and gamma rays. The distinctions between, or the boundaries between gamma rays, X-rays, ultraviolet, visible, infrared, and radio, different people will draw those boundaries in slightly different spots. So, when you're working on homework problems, however, I think it's important that you have a very clear understanding or image in your mind of what light is. And very early in the semester, I had you drawing these sine waves, or like a squiggle, a wave, to represent the wavelength. Now, for a few problems, I want you to draw a little more detail. Basically, I want you to draw this picture, where the electric field is going up and down, depending on where along the line you are. The magnetic field is going in and out depending on where you are along the line, and they should synchronize. So you can see the electric and magnetic fields point up and out, or in at the same time, and they point in and down at the same time. So, and then the distance between the peaks, either of the electric or the magnetic field, is what the wavelength represents. So when an electric field for a light wave or like a radio wave is described, what they're describing is the height of the longest red arrow. And when they're describing the magnetic field, they're describing the length of the longest blue arrow. So that's how you should draw this picture and then label electric fields as the longest red arrow, or the strength of the electric field is the longest red arrow, the strength of the magnetic field is the longest blue arrow, and if necessary, the wavelength is the distance between the electric field peaks. Okay, let's stop there.